Hello and welcome to York Observatory monthly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alumni Castle Observatory located at York University in Toronto, Ontario, Canada. York TeleTube broadcasts every last Friday of the month at 7:30 p.m. local Toronto time, right here on our YouTube channel. For any questions or comments you have about our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Instagram at the handle Yorku Observatory. We would like to inform you about the Summer 2025 Astronomer in Residence program. This program is a collaboration of the Alumni Castle Observatory in Killarney Provincial Park to host astronomers in the certified sky site of Killarney, to lead in-person presentations and shows using the park's observatory. Next week, Rachel Ward Maxwell will be at Killarney starting on September 1st, so make sure to stay attentive at our air blog during the next few days. To learn more about the program and check her blog, visit our website at yorkie.ca/science/observatory/air. Good evening, everyone. My name is Hector Jimenez, and I'm here alongside Mary Helen, Denelle, Anidia, and Artana from Alumni Castle Observatory at York University. We are excited to welcome you tonight, especially because we got a fantastic guest speaker, Nakul Sethuram, who will be diving into an interesting topic, role of interior solidification process on lava planet atmosphere. The observatory at York campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many indigenous nations. The area known as Toronto has been caretaken by the Anishinaabe Nation and the Haudenosaunee Confederacy, and the Huron-Wendat and the Métis. It is now home to many indigenous people. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. This observatory looks forward to continuing to learn and revitalizing our knowledge in this area. Now, let's see what targets are up tonight. Please, Artana, go ahead.
Welcome everyone. So before we get started with our main talk, we wanted to give you a little update on what you can see tonight. So today we'll be able to see Arcturus, which is one of the brightest stars in the sky. We'll also be able to see the star Vega, and as well as Andromeda. And today the moon is in its waxing crescent phase, and we'll also be able to see Saturn, which is visible towards the southeast. You'll be able to see all of these objects except the moon by eye tonight, but using a small telescope will always give you the best results. So now we'll move on to introduce our guest speaker.
Hi everyone, I'm here to introduce our guest speaker. Nakul is an undergraduate student at York University doing his final year in physics and astronomy. He has been passionate about the night sky since the age of 7 and dreamed of becoming an astronomer. He has been involved in outreach and research throughout the years. Over the 2025 summer, he has been working with Professor Charles Edward Bukhari on studying the interior dynamics of lava planets. During his free time, he loves to do astronomy, listen to music, explore the world, and do outreach and volunteering. Thank you so much for joining us, Nakul. The floor is yours.
Amazing. Hello everyone. I'm glad to join the TeleTube at the observatory tonight to talk about my research I was doing over the summer. And before that, I would like to introduce myself, like Daniel introduced. That was good, and I just wanna introduce myself again. I'm Nakul, and I'm doing my fifth year in physics and astronomy at York University. And over the summer, I worked on the project research, which is the role of interior solidification process in lava planet atmosphere under Professor Bukhari. And yeah, let's dive in. So what is a lava planet? So basically, lava planets are the planet that actually orbits close to the host star, and they're like tidally locked, which means they have a permanent day side and a night side. And due to that, the day side, since they're close to the star, and the day side is like permanently like facing the star, so the planet will have a high surface temperature, which is like around like more. It's expected to be more than 2,700 Kelvin, and due to that, what happens that like it's high, like the temperature is like high enough to melt the crust, so which ended up in a magma ocean on the surface of the planet. And some of the examples of lava planets, we can say 55 CNE, and then K2 141b, TOI 431b, and more. So when I said like permanent days and night side in a lava planet, how does it looks like? So this is how it looks like. So in the day side of the lava planet, we have the magma ocean here, and then the night side, which is actually cooled down. So that's why the night side is solidified, and the day side, which is like facing the star, and the surface temperature, which is expected to be high enough to melt the surface. So that leads to a magma ocean. But the other areas of lava planets, like the interior, basically the mantle, is expected to be solidified. Understanding the atmospheric composition, like something important to um to interpret like how the interior dynamics takes place, and especially like when we have the advanced telescopes like JWST, which actually help us predict the atmospheric composition of the lava planets through the spectrography. So through that we can understand, like we can like interpret how the interior dynamics takes place. So my research, so that's a question, like how do the interior dynamics help shape the atmospheric composition of lava planet, which actually takes me to my research goal. So my research goal is to determine how the solidification process can influence the atmospheric composition of the lava planet. So when I say solidification process, it's basically why do I consider solidification process, which is something when we go through the process, we could able to understand how significant the process plays a huge role in shaping the atmosphere of the lava planet. So solidification of magma oceans. So over the time, when the magma ocean starts to cool down, the crystallization process takes place. Crystallization is where the magma ocean starts to crystallize. So, which, and as we know, like the solid is more denser than the liquid. So the crystallized materials, like it's denser than the magma ocean. So what happens due to the gravitational instability, the crystallized materials started to sink down. So which is known as the phase separation. And another interior dynamic process which takes place in the interior is the thermal convection. So thermal convection is a process where it's a movement of material which depends on the temperature and the density contrast. So based on the phase separation and the thermal convection, we have two types of crystallization, like crystallization taking place um, in the interior of the lava planet, which is the fractional crystallization, where the velocity of phase separation segregation is greater than the velocity of convection. And for the for the batch crystallization, which is like the opposite, where the velocity of the segregation is lesser than the velocity of convection. So to understand how this process, takes place, I use the supercomputer Narwhal to run the simulation, and I use Core Bambari to run my simulation. And in the simulation, I particularly consider like some key parameters, which is the Rayleigh number. The Rayleigh number is actually which is based on which is the order of the convection takes place. So basically, and I took and for the entire simulation which I was like running, I considered 10 power 7 because the lava pad is viscous. It's like less viscous due to its high temperatures. So the convection is expected to be vigorous. The melt mobility is basically the efficiency of a solid liquid segregation, and for that I have chosen 10 power minus 1, 10 power minus 2, and 10 power minus 3. So in the graph over here, we could able to see like how the fractional solidification and the batch solidification differs based on the melt mobility and the Rayleigh number. So we could able to see if the melt mobility is greater, it expected to be on a fractional solidification, but if the melt mobility is lesser, which is expected to be batch solidification, and if we could able to connect this with the Rayleigh number, which determines thermal convection, we could able to understand what kind of solidification we can expect. So for the simulation, I used sodium, silicate, titanium, and FeO. And so why do I use this element? So basically, so those are like considered based on Earth-like composition. The reason why, because Earth is a well-studied planet, and also rocky planets are expected to close to have Earth based composition, and it'll be like helpful to understand the how the process takes place. So this is like a simulation, just like I would like to indicate in the simulation what exactly it tells about. So on the top left corner, we have the day side crust, which is a magma ocean, which is melted. And on the top right, we have a night side crust, which is solidified. And then the center, we have mantle, which is also solidified. And at the bottom, we have core mantle boundary, which is like the boundary between the core and where it's like a boundary of interaction between the core and the mantle. So this is sneak peek of a simulation of the silicate with the Rayleigh number 7, and the LComp is basically melt mobility, which is 10 power minus 2. So we could able to see there's a difference in composition, and as I mentioned, like the composition one is actually normalized to the normalized as same as the Earth's composition, and we could able to see the mantle has a different composition of Si. The day side, like in the crust, has a different composition, especially in the day side and the night side, and in the core mantle boundary has a different composition. So one more thing which we could able to significantly we could able to observe here is the circulation process. So what is the circulation process? So what happened? So I just go. Let me just go back to the image of yeah. So in the day side, when the magma ocean travels to the night side, it started solidified. When it's solidified, due to the due to the temperature, due to the density contrast, it started to sink down, and then when it reaches the core mantle boundary, due to the high pressure, so as the temperature started to increase, so the density contrast started to decrease, so it started to rise in the day side. So that's how the circulation process happens. So the circulation process helps to make sure it makes sure like the materials from the night side is being like added to the day side again. So it just goes as a cycle. So so we could able to like see the circulation process efficiently here. We could able to select the different composition and it looks, we can efficiently observe the circulation process. And this is for the Na. We can, and for the sodium, we could observe the same scenario. And for the titanium, also we could able to observe the same scenario. And the FeO is also, we could observe the same scenario. For the FeO scale is actually not based on the Earth-based composition actually, but we could able to see there's a difference in composition in the crust mantle and the core mantle boundary, and we can also significantly able to see the circulation process. So yeah, and so now we are going to the silicate where the melt mobility, and now the melt mobility is like kind of even more lower, which is 10 power minus 3, where we could able to see it's like homogeneous everywhere, like compared to the LCOM 10 to minus 2, where we can able to see this like a differentiation can be observed. But here with the 10 power minus 3, it literally looks homogeneous. And also the circulation process also is not like significantly observed because the interior of the planet looks really homogeneous. And this is also being observed for sodium, titanium, and also for FeO. So from this, what we could conclude is basically the interior solidification process plays a first order role in characterizing the atmosphere, and how we could characterize the atmosphere based on the solidification role. So from the simulation, where if we could able to like to characterize the what's the further process basically, like from the simulation, if you could able like to characterize the composition evolution like by like averaging it, and then if you could like understand, if you could able to link with the melt vapor equilibrium, which is like another process where which is actually it's a process where we could able to understand like the evaporation of the materials from the magma ocean. So we could able to understand that, and based on that, we could conclude that like if the interior has a batch crystallization, which means atmosphere will be like way more homogeneous with the process both volatile and the refractory materials. What I mean by volatile materials, basically volatile materials easily evaporates, where the refractory materials resist heat. So volatile materials mostly found in the crust, and the refractory materials which are denser is expected to be found in below the crust. So if the interior remains homogeneous, which we expect that like the atmosphere is also expected to be homogeneous with the presence of both volatile and refractory. And volatiles are basically sodium, and sodium is like highly volatile, and silicate is moderately volatile, and titanium and Fe are refractory materials. So if you have fractional crystallization, that the elements, the materials are chemically differentiated. So we might expect a chemically differentiated element, so a chemically differentiated atmosphere with the with high presence detection of volatile materials. And I guess it's time for some questions.
Right. Thank you so much, Nakul, for that incredible talk on the lava planet dynamics. We really appreciate you sharing your time and knowledge with us tonight. If you don't mind, we have got a few questions lined up for you. Let me ask first. First of all, why were these specific elements considered for the simulations? Can others be considered?
Yeah, so the reason why we consider those elements, especially as I mentioned, like we go for earth-based materials because rocky plants has like same composition, like maybe like some difference does even observe, but we use the earth-based because to understand how the entire process goes on, which easily helps us to understand and how these elements, how we got these elements. Basically, imagine if a rocky planet or a lava planet which has Earth-based composition is like close to the host star and how and those elements has been picked up based on how the atmospheric direction would look like. It's like more of a simulated one, and based on that, we got that we had a high absorption direction of silicate, sodium, titanium, FeO. We also had a high detection of MgO, Mg and MgO, and also we also had a detection of aluminum and like so on, like some other volatile and refractory materials. So apart from the materials which I've shown in the simulation, we can use Mg, we can use aluminum. Mg means magnesium basically, and we can also use aluminum and yeah. So we can also we can also consider calcium too. So those could be a next state of element which we could consider basically.
Oh, wow. Excellent. Oh, it's very interesting. Thank you so much, Nicole. Yeah, it's very interesting how these elements can lead to pretty interesting results, even if it is for exoplanets. So it's actually really amazing. Thanks for sharing that and clarifying. And now let me ask you another question. Regarding the whole research, what will be the major long-term goal for this research you are doing?
So this research is like not so it's just like interconnecting from the observed of atmosphere um, data. We're just interconnecting with from that we are connecting that with the how the lava planet interior dynamics takes place, and as mentioned, the solidification process plays a first order role, and then it connect the solidification process with the like solidification processes like solid liquid segregation with the melt vapor equilibrium, and then from melt vapor equilibrium we just connect with the again atmosphere to make sure you know it makes sense with the observed atmospheric data. So it's just basically like is the goal is just make sure we are interlinking um like each process so that like the and yeah, so like interconnecting the interior dynamics and atmosphere, like this help us to understand way more how the you know how it actually plays a role on shaping the lava planets.
I see, I see. Interesting. Thank you so much, Nicole. Now, Arsana also has some questions, so please, Arsana, go ahead.
Hi, so first of all, thank you so much for your presentation. It was very, very insightful. And this question is a bit jam-packed, so I hope that's all right. But my question is, and if not, can some of your simulations be based on the volcanic activity that goes on in one of Jupiter's moons, Io? And is it too far away from our sun? And do the interior dynamics of Io make it not suitable for a simulation of tidally lava planets?
So just in case if I miss, so this simulation in the code bumper is actually based on a multi-phase thermochemical fluid dynamics, which actually implements a multi-phase flow of mathematical formalism or the averaging method. What this exactly mean is the core boundary is developed to model the planetary interior process, which is actually based on the thermochemical fluid dynamics, which includes thermal convection, solid liquid segregation, and chemical differentiation. So the simulation, like the core boundary, is actually used could simulate simulate any for rocky planets, so which could also include the moons of Jupiter. So even though if it's like far away from the sun, like the code is not just only for lava planets, it just can be like altered for lava planets, but it can also be altered for like other based planets like um like the Jupiter moons as well. And this code is also used for like simulating the history of the interior process of planet Earth as well. So like how the interior process shaped the planet Earth over the time, and also for the moon. So the code is actually based. It can be like it can be like it can be used to understand the interior process of any rocky planets, which is like, of course, it's based on the fluid and the thermodynamics.
All right, thank you so much. So my second question, what are some disadvantages of the simulations you currently use, and how can they be improved upon?
So as I mentioned, from the simulation, we could only able to get the first order information. So the first order information is basically it just gives, like, we could interpret how it's going, how the entire process takes place. But there's also like second and third order interpretation, to make sure how exactly the entire process happens. So the limitation of the simulation is we could only able to observe the first order, only the first order simulation, which is actually sufficient to understand. But we can't able to go way more deeper into that.
Thank you. So, these like second order and third order like simulations, do they require more time to run? As
It,
yeah.
it's more of time, like the second and the third order simulation includes a lot of scenarios, like like a lot of other the areas of physics and geophysics needs to be considered. So that's what I mean by the second and the third order.
All right, thank you so much.
No worries.
Hi, Nakul. So thank you for this very interesting presentation. I've always been fascinated by exoplanets. Now, of course, over the last couple of decades, we found an awful lot of exoplanets of many, many different types. So you mentioned a couple in here, but how many have been found, and sort of what kind of population do they think of exoplanets are going to have atmospheres that are due to this magma and molten surface, and will have these kind of characteristics you've talked about today?
So so of course, with the advanced presence of the telescope, we might indeed, like, there's like a lot of the we could, like, like JWS, like it's very easy to like detect you know like lava plants, and still the process going on. And the when it's come to the atmosphere, like all the lava plants are expected to have atmosphere, because as I mentioned, like the silicate is getting vaporized, so which end up like forming a thick atmosphere over it. So, and also, like, apart from what I mentioned, like some other exoplanets which I get so some other lava planets which I could share about is the COROT 7b, which is actually one of the earliest known lava planet, and the other one is Kepler 10b, and also the other we can also, as I mentioned about Earth-based planet, we can say 55 Cancri E, which is actually a super Earth, which has been described as a sparkling sky and a rolling lava seas. And the other one, which actually likely considered to be a lava world, is Kepler 70b. And all those lava planets been observed with the JWST telescope.
So the other question I have is, of course, when we look at Earth, early on in Earth's history, maybe not for quite the same reasons, but as Earth formed, and probably as most planets form, the surface was most likely molten. So do they think that studying these lava planets can tell us something about Earth's early history?
Yes, of course. So as we were talking about the lava planets, once while even Earth was filled with magma ocean, but over the time it got cooled down. And for Earth, it's like was since Earth is not tidally locked, so the process of cooling down was way more easier. So not way more easier in the sense like it's way more uh, you know, you know, the loss of heat was way more higher than the planets just like tidally locked and close to the sun. This is close to the star where and if it's permanently locked, this the heat loss in the day side is negligible because the day side is receiving a lot of heat, and then the night side is basically is where the heat loss happens. So, but planet Earth actually spins. So over the time, both the day side and night side loses heat. So the process was way more faster. So the lava planet dynamics also indeed help us to understand the um how the process of the earliest years being taken place, especially like understanding the solidification process. I remember instead of the solidification process, if the if the planet starts to cool down more and more, the thermal convection started to slow down, which means the solid liquid segregation takes over, which leads to a fractional crystallization.
Thank you.
Hello, thank you for your presentation. It was wonderful. I had a great joy hearing the presentation. Uh, I have a few questions for you. One of the major one that this question is, how do astronomers detect and confirm that an exoplanet has molten surface?
Good question. So it depends on the direction of the species in the atmosphere, and also the distance. Like the distance can be calculated through the transit curve. Like we have advanced curve, as I mentioned, like DWST, like it's easy to get like transit curves of rocky planets, and the direction of species from the atmosphere, like the spectra of the atmosphere also tells us like for lava planets, as I mentioned, like the temperature is high enough to vaporize silicate, and like sodium, magnesium, some other refractory elements. So if you have like that, the direction of silicate, sodium, and other refractory elements, so that confirms that it might have a molten surface.
Oh, that makes perfect sense now. My next question to you uh, is why I know that a bit on your presentation, but if you could explain it in more detail, like why are most lava planets tidally locked to their stars?
So it's due to the tidal force from the host star. So when we take the moon is actually tidally locked because moon is like proximally very close to Earth, and due to the Earth's high um, tidal force, the moon actually you know so the moon's actually like it's been like tidally locked so that like you're only able to see one side of the moon. So the same goes to the object that's been close to a host star as well. So the one if the object is very close to a host star, the high tidal force prevents the object from spinning. So that's why which leads to the tidal lock of the planets.
Hey, for your answers and your time and your presentation.
Yeah, thank you so much. Was glad, and yeah, thank you so much for having me for tonight. Oh, we have okay, sorry.
Yeah, we have
Yeah.
more questions. My question is, do we think lava planets are common, or are they more of a rare type of world?
It might be common too, like so it depends. Like this universe is very big. The detection which we have made might be lesser than compared like the other like gas giants and stuff because our planets are very hard to detect because they're very small. And also they're like approximately very, very close to the Earth star. Like if you consider Mercury, Mercury is like very hard to detect, like with our naked eyes or even with the telescope, like it might be we can like easily detect them. So detecting lava planets might be hard, of course, but it's more or less could be like we can't like say it's like more common or rare, so it's like should be somewhere between for sure. But
Okay.
for the amount of lava planet which we have detected should be less because as I mentioned, detecting lava planets is not that easy.
Okay, thank you. My next question is, are AI or machine learning methods being applied to model processes such as magma ocean solidification?
So okay, that's a good question. So just I feel like we never used AI or machine learning for this project which I have been worked on, but it could be a good tool like especially like machine language and AI is more of like interpreting like it's more of like and it's pattern based rather than simulating. So I am pretty not sure that machine learning or AI could be used for modeling process. Like it could be like used for like detection based or like more of like pattern based kind of thing. But
Yeah.
more for modeling based, I think AI machine learning is still not a good one.
Yeah, that makes a lot of sense, actually. Thank you.
Yeah, no worries.
You have been listening to the Alani Carswell Observatory's monthly TeleTube broadcast, brought to you by the Astronomy and Astrophysics program, which has been written and presented by the students, faculty, and friends of York University. The host this evening were Hector, Artana, Professor Mary Helen, Danielle, and I. Make sure to leave any comments or questions in the comment section or live chat. We will be around the next 20 minutes to answer your questions. All our programs are free, but if you would like to make a donation, see our website yorku.ca/science/observatory. You can always connect with us on PixelFed with the handle @York Observatory and check out our website for show notes, content updates. Thank you for tuning in. Clear skies and have a good night.